you have to look for a dimensionless ratio being small, or of course you can invert that saying it's much larger than that. So every approximation has to be some dimensional ratio alpha. A simple point, but I think a large majority of, I have been also a teacher, and we don't state these things, we take these for granted. And but our finding is most students in higher education stages, even sometimes the very good ones, sometimes slip on this point, or have not really internalized it. This is the sample question. I have called it sample question because it is not exactly the question. It is exactly the same thing and nearly everything, but some words have been changed because it won't fit in the slide. The content of the question is bigger than it was. Okay. So the question is, restoring force is approximately linear during the entire motion. If the displacement x is small, constant k dash is much smaller than k. Both k dash and x are small. The amplitude a is much smaller than root k. A large fraction of students opt for ABC, not B. That correctly identifies the dimensional ratio. Yes. You see the important point, and these are senior BSc students. Because the test was slightly mathematical, we said no, not beginning. I mean, MSc Part 1 students. A large fraction of them are opting for A, B, and C, which to a physicist are meaningless because these are dimensional quantities. So what is meaningless for us after a lot of experience in teaching or in research or whatever is not, the message is, it's not obvious to students. It has to be explicitly told. And unless you tell that, people are going to make these errors. Of course, once you tell them, they will easily agree. So that's the point. We have found in many other, even advanced physics research, that they make mistakes, but once you tell at least the meritorious student, they immediately get it. So, uh, next thing is the notion of the order of approximation. This again is not very well known, and although it's taken for granted by physicists, the notion of order of approximation is a way to deal with approximations in precise terms. It's not enough to say some dimensional ratio is small. We need to say what terms onwards we are neglecting. If we neglect alpha to the power n plus 1 onward, the approximation is correct up to order alpha to the power n. Now, this seems obvious, but importantly, in this case, the approximation is correct to order alpha to the power n, even if its coefficient is identically zero. This is not well known even among teachers, I should say, and even among physicists might make this thing out of the slip. It's not that they don't know the concept. Because our tendency is to, wherever the expression is ending, we call that the order. But the correctness of the order of approximation the error starts from what you're neglecting. So it is correct up to the order which has not been neglected. Now, just by identically its coefficient is zero, that doesn't change the order of approximation. A very important point. For example, in the series expansion of this, writing theta, most people will say it is correct up to first order, but that's wrong. It is correct up to second orders, because I have not neglected theta square. It's identically zero. The coefficient is identically zero. So by putting sine theta equal to theta, I am making error from third order onwards, not second order onwards. So if I have to add this to supposing this expression comes in addition to sum of other terms, which have been expressed up to order theta square, supposing it has been ordered, they are correct, and they have non-vanishing theta square term. So will it be correct to add this term to say and still claim, yeah, my result is correct up to order theta square? Yes, because I have not neglected theta square. The other terms may have non-vanishing theta square. Here I have vanishing theta square, but that's not my fault. That's in the expression. I have not neglected it. So it's correct. It's a very important point, not very well known in the physics. Not very well emphasized. Once you say this, of course, everybody will know. Of course, sine theta as these power c is always, this has nothing to do with this theme. We should note that, and we should tell students that the argument of a transcendental function, like, Bessel functions or sine function or whatever. So there are so many special functions in physics, and even a polynomial with dimensionless coefficients. The argument has to be dimensionless, otherwise it won't make sense. Only a monomial can have dimensional order. So these are some of the most important points. So this is the theme 2 thing. Just wanted to see what is the prevalence of this error. And you have this simple formula for relativistic kinetic energy, and it's up to a certain order is Newtonian kinetic energy. This is a correct approximation for kinetic energy. Yeah. I'm just seeing time. So this is up to order V by C, V square by E. This question reveals a truly widespread pitfall. I mean, 93% of people, sorry, I should have mentioned that I have, because of the lack of space on the slide, this means 93% of students have this pitfall. And 70% of the students actually say B. It's a very common response, V square by C. Very, very few people say it to be V2 by C2. So this is another bit. Now, third is approximations may have this. This is a slightly more difficult, not conceptually difficult, but technically difficult theme. But we wanted to handle it. So there are so many situations in physics. For example, Einstein's theory, when we say it reduces to Newton's theory, there are not one, but two approximations. One is V by C is less than 1, and the other is weak field approximation, as they say. So the GIK, the usual metric tensor, is eta ik plus hik, and hik is small compared to eta ik in the notation of, metric tensor. But this is a little advanced, but more familiar example is the van der Waals, which appears in all undergraduate physics. So here, of course, we should not say with A and B are small, then it reduces to that's meaningless. We must identify the ratios when the ideal gas equation in this thing is small. B by V is small, and A by RVT. You have to properly work it out, and it comes. It's can be done orally. You just take V outside, so it will be 1 minus V by V, so it will be A by V, and A by V should be smaller than P. So A by PV is the dimension ratio, sure, and PV up to first approximation RT. So these are the quantities that are small. So saying that it is reduces when A and B are small is a careless statement. It's often made even in classrooms. Even I might have made this statement. So I'm not saying that in a hurry, because if we are doing something else, we don't stress the points of dimensional ratios often in our this thing. H cross is small and things like that, and C is large. These statements are careless statements made in classroom instruction. This is the slightly difficult question. A body is moving with speed u on the equatorial plane. We have made equatorial plane to get rid of latitude terms, etc., thetas, etc. And the acceleration of the body towards the center, the velocity is such that it's towards the center. Coriolis is either towards or away. And of course, we know centrifugal force is always away from it. So this is the thing. It's a standard result. And then there are various options. And the correct option is D. Both the Coriolis and centrifugal are negligible if you use this. Now, once again, it is so trivial. I mean, just to say these two things are small, you just have to compare, get a ratio, and you will get U is less than G by D, and omega should be this. It should be put in the form where at least the Coriolis, U is in your hand, G and omega and R are not in your this thing. So centrifugal acceleration has a certain value, and you can't do anything about omega. But for a planet, that's why we did not say Earth. For a planet which has this condition satisfied, then the Coriolis and centrifugal accelerations are negligible. The pitfalls were similar to T1. I must say this question has not, its design is not very good because we tried very hard, but its difficulty level we could not reduce. And therefore, when difficulty level is not reduced, then what happens? The results are not easily interpretable. So 0.38 opted for, we can't say whether they really understood it or it was just this thing, because there was no clear cut because of the difficulty of the question. What happens is the moment you put little more maths in the question, a large number of students just refuse to think. So it's not a problem that they do not understand this aspect or that aspect. It's that they're just refusing to deal with the question. So therefore, this question is a bit not properly well defined, and it's against construct validity of the question. But I mean, that is from the point of view of PR, but I think from the point of view of instruction, see, there are two messages in this lecture. One is PR, where, of course, I have to criticize the test, etc. The other is its pedagogic values, where it doesn't matter how we have, we just understand that the student should give this answer. So I hope I'm clear about this. There is one pedagogic use of this paper. One is it's standing as a PR paper. These are two different matters. So next thing is order of approximation. If we claim an equation is true up to a certain order, I have already told you, each term must be, I think this theme is consistency of the order. Each term in the approximation must be correct. It's an obvious statement. Also, knowing a few terms up to alpha cube or higher in this case does not improve the order. The order of the least precise term determines the order chosen. For example, relativistic corrections to Bohr's theory of hydrogen is V square by C square times the uncorrected energy. If you do Bohr's theory and do relativistic correction, as Sommerfeld did. But to refine Bohr's theory consistently to that order, we must take care to include all known corrections. That won't help, only doing one. And these other corrections, now we know, there's a lot of interesting history about it, and are the spin orbit coupling term as well as the effect of Thomas precision term. So you see, for alkali atoms, for example, what happened was historically that Sommerfeld succeeded and he explained the fine structure, but then his formula was true even for alkali atoms. Then people got suspicious that this is not a correct explanation, and therefore then they looked for, and that is how the discovery of this spin happened in history, and spin orbit as well as Thomas precession. This is because the spin of the electron, I mean, in the lab frame, there is no magnetic field. So what will it interact with? What will the magnetic moment of the electron interact with? So one had to go to the electron frame where there is a magnetic field, because there in that frame the proton is orbiting. There is a magnetic field, etc. So I mean that's irrelevant to this paper. But what I'm saying is that, I mean, in history also these points about order of approximations, etc., have played a very big role. So we have this acceleration of a charged particle, uh, and then up to this order, this acceleration is given. You see, this is the usual thing. I mean, which we all do in class. This is the Lorentz force, and A is the relativistic mass. So this I'm not one minus. So Q by M, P by C cross V. This is the standard Lorentz force. This is in some theory which includes radiation damping, etc. So it's a very complicated term and not a very well established theory, but we had to construct some question in this. The second term divided by the first term is given to be of the order of P by C. Now the point in this question is this whole surrounding maths is quite irrelevant. You can orally see that dA by dt is V by C into this term. So dA by dt is V square term, V square by, V square by C squared term. So it's second order already dA and V. And this is first order. But as I told you, if I put V, if I expand 1 minus half as I have done here, then it is going up to third order. There's no point in putting third order because dA by dt is second order. So this is unnecessary. The first answer is correct. And the first answer, the first term is correct up to V square by C square. dA by dt is of course V by C square. But the first answer, this first term is correct up to second order. I hope I'm making myself clear. It's correct up to second order because the error starts in the third order. So it's a perfectly correct statement in physics that A is correctly given by this expression up to order V square by C square. So these are some of the points which are not told, though experts and teachers are well aware of them. Most people can't correctly count orders in multiplicative terms. Well, it was difficult to analyze this question. And our hunch is, we cannot say, is that the students just get confounded by the maths that, oh, this is too much of maths, etc. There's hardly any maths, etc. You just divide this by this, the square root cancels, and it immediately tells you dA by dt is of the order of V square by C square. And that's all, period. After that, just mere counting of orders is necessary. But just the look of the mathematical look of the question is putting some students off, which is why there's such a poor response to this rather trivial question. Every question in this thing, if to a person who knows it, is an oral question. You don't need any paper, pen, paper, or at most you might need a line on paper and using paper pencil. Next idea is when two effects come together, fairly independent effects, though they might couple, but fairly independent, when they couple, then what to do about it? This situation often happens in physics. A common strategy is to include one effect, ignoring all the rest, and then simply add up the corrections due to each. This yields the leading correction to theory due to all effects. So this is a strategy, and it is based on, it's not very rigorously justified, but it is based on a sense of order. And the sense of order is that to first order, if you do two things, the coupling effect will come in the second order. Suppose we want to correct larger amplitude and air resistance to the standard formula where there is no air resistance and small amplitude. If the correction due to one is alpha T naught and due to alpha beta, then the leading correction due to both is alpha plus beta. That is the usual physics strategy. The rationale is that any coupling of the two effects is likely to involve alpha beta, which is of higher order than alpha beta and hence does not contribute to the to the leading correction. We are assuming here that alpha beta corrections are comparable. I mean, beta is not of the order of alpha square, then even beta is not necessary. So alpha beta, the implicit in this is alpha beta are comparable, and then alpha beta will be naturally the higher order. So some judgments are going into this. This is not as rigorously founded as the earlier ones that I found, but generally it is done. Because a critical person say, why not? It could be root of alpha beta. The coupling effect could be root of alpha beta, in which case it's of the same order as alpha beta, etc. So people can argue that way. But in our paper, we have advanced some argument why this is a very famous example of Einstein's correction to Mercury precision. So, consider the motion of a planet around a star. If the gravity obeys inverse square law, a lone planet moves on an ellipse, as we all know. The ellipse precesses due to the effect due to other planets around the sun, and the effect due to a more refined theory of gravity. We are referring to Einstein's theory. If only the effect of other planets is considered, a first order approximation gives the precession angle to be this. If only the effect of the refined theory is considered, a first order approximation gives phi 2. Take phi 1, phi 2 to be of comparable order of magnitude. So we are giving that in the paper. With both effects, the first order estimate of the angle is phi 1 plus phi 2. Phi 1, phi 2 is none of the above. All estimates are unreliable since 1 does not take into account 2 and 2 does not. So D is quite the correct option, of course, is 1. Fourth is quite a appealing option. And only 0.31 seem to appreciate the decoupling of the two effects and hence neglected in this. So, in fact, this is exactly what Einstein did in his famous calculation of Mercury precession. The phi 1 had already been calculated, but the experimental value fell short of by some 41 seconds of arc, etc., etc. From the experimental value. So Einstein supplied phi 2 due to his gravity, the new theory of gravity, which he approximated. Of course, it was not an exact solution. He approximated to the leading order, and he got leading order just very near to what was required. So phi 1 plus phi 2 was experimentally. This was a famous, great success of Einstein's theory of general theory of relativity. So this is the thing. But we don't need to go to these advanced domains to tell this. We can do smaller, more simpler domains. The last theme is, again, very important in my view. You see, it's almost based on, all of us have gone through calculus-based derivations, etc. And at least as far as I'm concerned, I used to be confused about this point in my student days. And then we got clarified later. So these calculus-based derivations involve many small quantities, which in the limit go to 0. So some of the small quantities are dropped right away, and some are retained till the end. Some may involve approximation like sine theta, etc. So in a calculus-based approximation, a lot of things are dropped, but some are at the end retained because you have to do the calculation up to first order, etc. So do these approximations and neglect of different small lead to approximate or exact result? It's a natural question for even a good meritorious students that we are dropping something. I'll give you the example. The answer is that that when the small quantities become infinitesimal in the limit of them going to 0, the result of calculation-based derivation is correct. Also, a very important point often missed out is that the ratio of the higher order infinitesimal to a lower order infinitesimal. goes exactly to zero. That's why we don't even consider it at the beginning of the calculation. I'll give you an example of this. Thus, the notion of order of infinitesimal is a very useful practice for physicists. But I must warn that mathematicians don't like the way we are talking about this because they are concerned with other matters, and therefore uh, they have to go by their strict method because their proofs don't involve such notions of infinitesimal. Now, proof of expression for area and velocity of a particle. Uh, so I'll give you the proof, and it's very almost a trivial proof, and uh, you will see that what I'm saying. So particle moves from P to P dash in time delta t. It's a plane. Particle is moving in a plane. Here's the origin. Draw perpendicular to OP dash. PQ perpendicular to OP. This. So for small delta t, the area covered by the portion PQ dash is negligible. This is what I meant by saying that you just drop it without even telling why you are. Everything is negligible. Even this is negligible because these quantities are going to go to zero in the limit. Then why are you? What is the justification for neglecting this little shape of? It's not an exact triangle. This arc and two lines of a sort of triangle. You're just right away dropping it. What's the justification? And then we happily say where area of triangle OPQ is half r square. So we, base into height. So base is r cos delta theta and height is r sine theta. You have this. And this actually is sine 2 delta theta upon 2. And sine 2 delta theta is 2 delta theta upon 2. So you just get delta. So it's again an oral calculation, hardly needs any mathematics. Thus the area swept in time delta t, this was delta E, is half r squares. So in the limit, what will be the aerial velocity? Del A by delta t is delta theta by delta t. You get this result. This result is related to second law of Kepler's that aerial velocity is constant, which actually means angular momentum is constant because angular momentum is related to aerial velocity by just a factor and so on, etc. So what is the justification for this PQP dash? The justification, which we rarely tell I don't think even I have ever told this in my class, that this area is a higher order infinitesimal. Our calculation is calculating delta E, delta T. These are all first order infinitesimal. But what is the area of this? Just see, this is R sine, R sine theta, and this is nearly dr, which is actually dr into 1 minus cos theta, but cos theta is up to first order 1. So this is R delta theta. So there is one infinitesimal here, and this infinitesimal, this is also dr. So product of two infinitesimal is higher order infinitesimal. So the area of this divided by this small one of first order infinitesimal exactly goes to zero. So we are not making any approximation in dropping it. It's an exact result. So I think we should tell in our instruction that of course we are dropping it because at the end we are going to retain only a first order infinitesimals. So, and this is a second order infinitesimal. So it can be dropped exactly. There is no limit. It's an approximation as long as we don't take the limit. At the moment we take the limit, it's an exact result. So this is the point we wanted to think. So we gave some options. This cannot be an exact result since we are neglecting the area, which may be small but not zero. This is a thought which will come to students' mind. This cannot be an exact result since sine delta theta is equal to is an approximation. See, in this, when the student is doing pendulum sine theta and say, we all say in the class sine theta equal to theta is an approximation. But here we are not saying it is an approximation. So the student is naturally thinking that it's an approximation. This cannot be an exact result in both the reasons. This 3 appeal to many students. For planar motion, this is an exact result, no approximation. Only fine for students go for the correct option. A significant fraction, about 0.3, goes for the appealing option C. So this appeals to many students. 1/3 of students go for this. And in fact, I was happy that we got so many votes, but a little thought shows that it's not very clear because the design, again, is a defect of the design of the questionnaire, that it prevents us from knowing what fraction of those going for the correct option, particularly here. Did so because this result is very well known. You know, people do Kepler's second law, so L is 2m dA by dt and L is conserved. So these results are sort of known. So, but the design of this study should have included interviews. We are well aware of it. But interviewing these 141 students was an impossible, feasible task. They were not in the same city. Although we had interviewed the pilot study students very thoroughly, we could not interview this. So that is a limitation of the design. So finally, the data. The mean score was 4.06 out of 14, showing that students performed poorly compared to the usual contents. Their usual content score was something like, normalized to this was something like 11. The students whom we also asked their scores in higher secondary and first year BSc, second year BSc, and we got some average. So this has to be compared with something like 11 merit test. So clearly showing that this is a new kind of test. This is not the usual merit test. There are several statistical measures. All the statistical methods, they are all given in the paper. Reliability coefficient, that Cronbach alpha coefficient, and then the consistency patterns also. Whether the same student who made mistake, as I told you, there are pairs of questions, each with the same kind of pitfalls. So if a student is making pitfall here, does he or she make the same pitfall there? So we developed a measure for that. The measure was reasonably good. 50% students showed that consistency. And this is quite a good number because if it was all random, then there are very large number of combinations and you would not get the consistency index will be just 10% or so. But we got 0.5%. Our reliability was slightly less than what is regarded as good. We had 0.65, and similarly, Cronbach's coefficient was 0.64, something like that, slightly less than this. This is because of the mathematical difficulty of the test. So it's a great challenge for all of us who are doing PR at the college physics education, because physics does become mathematical if you want to test some higher domains. It can't be just qualitative. And on the other hand, it has to be made less and less mathematical. How can you do that and still do that? It's a challenging thing. We succeeded only partially. We have not succeeded completely. So some of the findings I have already told you. The use of small or big qualifiers for dimensional quality. No awareness of dimensions ratio. Judging the order of the approximation by the last term that you end up with, not by the order one less than, which is the correct thing. They are unable to deal with approximations with 2 or more parameters. They don't have a clear-cut meaning of consistency of the order of approximation. There's no point in doing higher order terms when some other term is lower order, etc. Inability to count order. This was a surprise. They can't count order of approximation in product terms. And regarding the neglect of higher order infinitesimals in calculus is an approximation. So these are some of the findings. More details are in the paper. In general, the idea is students view approximation as clever tricks to simplify calculations and get the expected results. And for them, it's like tricks. They don't see that there is a very clear rationale for this practice. And there's a quantitative meaning of order of approximation. Finally, the study has direct pedagogic implications. The key aspects of approximations identified here appear implicitly in numerous contexts. As I told you, it is just everywhere. And yet, as the results show, even meritorious students are not aware of these little elementary points. So our recommendation is they need to be an explicit part of undergraduate physics. I mean, one should set aside, or at least while doing an approximation, one should emphasize this point and not take it for granted. And the other thing about this thing is that we design our own questions. I mean, different teachers can define their own questions. It's a very generic thing. It's just a template we have given. People can design their questions and have students practice them. And I believe good teachers who are very experienced and also physics PR researchers, they can improve our questionnaire. I think it needs improvement in terms of construct validity. And I believe that if you do this, because approximations have a lot of connection with history. So it's not just some clever trick. And then that it has a very rational basis and go a long way in enhancing. For example, we say in relativity, the experimental rejection of ether needed V square by C square effect. V by C effect. You know, ether, even if ether was moving or not moving, an experiment that determined only up to first order V by C was not good enough to reject ether. This is because even the Lorentzian old theory could somehow manipulate the V by C effect. But it was the V square by C square effect. So it is which finally settled that the ether is. So it has very profound implications in history, etc., the order of approximations. Of course, what I'm saying is that this will improve their appreciation, etc. These are intuitive conjectures. Some PR. So what we have done is diagnostic studies, and we have done PR study on the extent of findings. Now the claim that this should be explicitly taught in pedagogy, in our instruction, and that it will be useful is our intuitive claim. We have not proved it. A PR study is needed to prove it in controlled experimental. And we believe that if you need this elementary, they may be sounding very elementary, trivial, but I can tell you even most important, I mean, even higher order approximation, you need to have a clear sense about these points that I just told you. So it will prepare the student for more advanced. So that's all I have to say. I would like to thank my colleagues, Mashood and Anvesh Majumdar, for very still. We have been doing PR for the last several years now. The epistemic things that I mentioned and others, some other disciplinary practices and so on. These are the references of the paper. You should go this. Paper 1 is not an empirical study. It actually explains in great detail the aspects that we have seen. And based on those aspects, this empirical study was carried out. So I would like to conclude by thanking IIPT and all the members, Professor Aluwalia, Professor Sapna Sharma, all the other IIPT members, and of course my friend Professor Vijay Singh for all the courtesy and kindness bestowed on me, in inviting me. Thank you very much. That's all I have to say.
Very good.
Thank you. That was a very fascinating
Yes.
talk. I found it very, very fascinating. And the way you put it across, except for certain examples, which involved some Lorentz force, etc., was very, very clear, Professor Arvind Kumar. I will
Thank
now
you.
leave it open to the audience to ask questions, but I will request Sapna Sharmaji to organize this question asking, because I'm very poor with Zoom. So thank
No,
you, Professor Arvind Kumar.
it's not like that.
You couldn't be as poor as I am.
No.
No.
Don't say that. So, actually, actually, if anybody wants to ask question, yeah, Mayank Vaya has raised his hand. Yes, Mayank, go ahead.
Mine is here. Yeah.
Yes, sir. Professor Arvind, that was a brilliant exposition. I just wanted to make one more point that in physics, we also do approximation because the quantities are not measured with the precision with which it is assumed. And that error adds errors that add approximations, etc. Would you like to say something about that?
Yeah, that comes into the domain that I said is hard. And you see, when you want to compare theory with experiment, then you have to, of course, first calculate within your theory what are the possible errors. And then you have to calculate within experiment what are the possible systematic, and what are they called random errors, etc., etc. So, I had restricted myself only to the approximations in theoretical physics. The task of comparing theory with experiment is very, very non-trivial, because as you very rightly said, you have to see the quantities that they are also approximate, and even our theory is approximate, and yet, but it has been done, I mean, to astonishing degree. I mean, the electron magnetic movement has been calculated, excuse me, in theory to, I don't know, some 1 part in 10 to the power 9 theoretically, and also it has been experimentally. So both have to be seen. Then you can say the quantum electrodynamics is correct, is theoretically is matching the experience. I entirely agree with you, Professor. That aspect, but that's too complicated an aspect. That's a real physics aspect. See, in PAR, as far as I understand, PAR, we have to cull out that thing that can be diagnosed with constructuality. The moment you go into very complicated and the real physics things, you don't know whether you're testing competence or you're testing misconceptions.
That is true.
It's a very big dilemma in advanced PAR. It is not so much in school level physics, say class 8, class 9. There the technical level is so small that if a student is making some responses, it is definitely his cognitive misconceptions and so on. But at the advanced level, if a student is getting wrong, is it getting, what are the reasons for getting it wrong? Is it just because he gets scared by maths? Is it just because he's not familiar with the context? You see, as many current cognitive science research shows that our epistemic frame is foreign. We may look very bright when talking about something like I'm rather familiar with this topic, so I might be looking, how much clear he is. But my epistemic frame is discipline specific. The same kind of thing I am put some other question in some other frame, I'll make mistakes. So therefore, is the college students' error due to context unfamiliarity, due to phobia of mathematics, or due to simple laziness? These are confounding variables of constructuality. And a peer researcher can only attempt to reduce them. At the advanced level, I don't think they can ever be reduced completely. Does that answer your question?
Yes, sir. Thank you, sir.
Professor Rajkumar Prashiri, sir, has raised his hand.
Yeah.
So, very good afternoon, dear sir.
Thank you. Yeah, good afternoon.
Very, very interesting account on the topic, and because mostly we are around understanding approximation in physics, so I come across a formula, the parallel combination of resistance, and when we and then wanted to calculate say error. So there are two different ways of going ahead with the problem. So for example, say 1 by z is equals to 1 by a plus 1 by v, and then take the log and differentiate and arrive to the conclusion that delta z by z is square is equals to delta a upon a square plus delta b upon b square. And another approach happens to be which we used to come across maybe long back. Like for example, you do first the simple calculation z is equals to ab upon a plus b, then take the approximation. In both the cases, the answer turned out to be different.
No, I mean, I don't know what you're saying. For example, so in any case, that is once again coming to the error analysis.
Yes.
This is error analysis of experiments. So anyway, so 1 upon r is equal to 1 upon. So what is r? R is r1, r2 upon r1 plus r2.
Yes.
That is what you should do. As far as I know error analysis, you take delta r and delta of this thing. So what is delta of r1, r2 upon r1, r2? You have to just, yeah, r1 plus r1, r2 upon r1 plus r.
Yes, very right, sir.
Yeah.
So the idea is, I mean,
So
you can have two different approaches, but answer got to be same.
take d of this thing. First, take differential coefficient of this with respect to r1 and delta r1 plus d. Take d of r2 into delta r2. That should be the correct answer.
So
What else can it be? But that's error analysis. I mean, if there are other subtleties, I don't know. What are you saying? I mean, what will you do? I mean, if you
say for example, say you have the formula 1 by RP.
yeah,
RP stand for the parallel combination resistance.
Yeah.
1 by RP is equals to 1 by R1 plus 1 by R2.
yeah.
So this is the formula.
I'll have to work out whether two methods are equal or not. I can
So this is what I have found a lot of difficulties explaining to student why we get different answers in these two approaches.
I'll have to see. I have not come across what you are saying.
Yes, sir. So this
Professor Vijay wants to say something.
Yeah.
Yeah, I have come across what you're saying, Dr. Parashar. One method is wrong, but let me just work it out and send it to you then. And
Okay.
this is
Yeah, I mean,
probably
you have to work it out.
something, yeah, even Professor Arvind Kumar can work it out and send it. And certainly he can work it
Yeah.
out.
We have
And,
to take by both
but
sides.
this is basically not the focus of what Professor Arvind Kumar was saying. I mean, so, okay, go ahead.
I would be surprised if
Professor
there-
Bhupati Chakravarti has also raised his hand. Can we
Yeah.
hear him?
Yeah.
Yes, sir. I have a simple question
Yeah.
that, for example, in the treatment of simple pendulum, we ignore the air resistance. Now, I understand this is an approximation, of course. Now, if we bring in the air resistance, then we need to model it, whether this is proportional to V or V square, that sort of things. So, I mean, that way, if we make that approximation that air resistance is not there, life becomes very simple for us.
Yeah.
I mean, doesn't that thing happen elsewhere also? For example, this amplitude case also.
Yeah.
If we really theoretically consider it to be small amplitude, but take the longer amplitude and work out. So these sort of approximations, normally we, at the initial stage, we tell to the students, but can you please suggest some way how we can gradually do away with them before the students and ask them, you see, this is the real life situation.
No, for air resistance, etc. Yeah, you are absolutely right. That it depends on the model, whether it is proportional to V or proportional to V square, etc. So that you will have to you know, you have to use some law. Maybe the Stokes law would say it's proportional to V, you can try V. But that's a model. So as far as the amplitude is concerned, it's a different point, because actually the exact result is known, but it's a highly complicated function. So you take up that function up to the next order in theta. So take the leading correction due to the exact result. Don't use the exact result, but due to the leading correction. So that will be a first order correction. And here also, when you add f6, I mean, whether v or v square, that you cannot do. That also you should take as a perturbation and get the result up to first order. Then you get the first order and add up these two corrections. That will be the first order approximation. First order correction to the t equal to 2 pi root by LH form. Now, I must say that with the arrival of these computational physics methods, things are going to be very different. There, you might feed that actually the exact equation, and as far as viscous law is concerned, you will have to feed a model, and then, I mean, you will get results numerically. There it will be hard to say whether it's first order, second order, etc., because you are feeding the exact thing. But analytically, you should always do only a first order and first order. You see, did I make myself correct? Exact for any angle theta, the exact result is known. It's just too complicated.
Yes.
So go to that function, take its leading term. For theta very small, it's going to be theta, but there are going to be higher order terms. Okay.
Just one point, sir, I would like to add. Quite often, I mean, this happens when we are doing the experiment by hand. Suppose that even if the angle of amplitude goes up to 30 degrees, there is apparently, I must stress, no deviation in the time period. That is because of our measuring system, handheld clocks. They cannot detect the millisecond order change. So apparently we feel that there is no change, but that happens.
Yeah, but there also I want to emphasize the fact that in simple pendulum, theta equal to reasonably about 15 degree or so, it's quite okay. We may feel it's a large angle, but it's quite, and the reason is what I mentioned. See, theta equal to 15 degree, how much of this is radians? Pi by 12.
Yes.
Okay, so pi by 12 is, so sine theta equal to theta. Now you take sine 15 degree. Now I don't have in
No,
the
sir, in 30 degree deviation is only 4
Even up to 30 degrees.
From 30
4%.
degree, 30
4%.
degree is not bad, because sine 30 degree is half.
And that is
Pi
0.5.
by 6. Pi by 6 is not too much away from half.
0.52.
It's just 0.52. So
0.4%.
and the reason for that is that the next term is correction term is theta cube. See, the reason why it works is exactly what I told you, that it is not sine theta equal to theta is not correct up to order theta. It is correct up to order theta square. And theta square is reasonably small even for 30 degree. So where it gets wrong is theta cube. And pi by 6 theta cube and sine of 15 degree, the correction is very small. See, the error is in the cubic order, and that's why it works very well even for 30 degree. Of course, very strictly speaking, there will be correction, and if your instrument can measure millisecond or whatever, then of course it will detect it. The error will be very, very small.
So Professor Aluwalia has raised his hand. Sir, please.
Very much, sir. I'm grateful for your lecture. I had just one thing to say about approximations when we do computations. there are certain things which happen in the background when we do computations, about which we are not sure what computer is doing. For example, rounding off which computer does
Yeah.
is very tricky, and that actually makes computations also an art, because how you keep track of that. And normally there also what uh, is done is that we try to go back to basic physics
Yeah.
and ask such questions as whether energy is being conserved or not, what is happening to different conservation laws in the process of computation itself. These are
Yeah.
very crucial questions which come in computation itself. And there is one more thing which I wanted to actually ask was this, that how do we take these studies of PER into the undergraduate classroom? Because there are certain studies which happen and they normally are not carried forward in the classroom itself. Sir, what is the way we can really move forward? Because IAPT community has, I think, a big role to play in these kinds of things.
Yeah.
What would you be telling us in what way we can move? Holding these lectures itself is, one way to encourage people to come forward and look at PR, things and use those in the classroom. But what would you really advise us, sir, in what way we can move forward?
Yeah, there are two questions. One is that numerical computational thing.
Yes, sir.
Oh, that's a very big topic. And in fact, I must say that I am currently trying to learn it because at now such a age, now I come to realize that I can no longer avoid computers. So for all my life, I was only interested in analytical physics, and I sort of kept away from computation. But now I have realized that it's not something. So I'm trying to learn computational analysis at my own slow, relaxed pace. So I agree with you also. I mean, there are very clever techniques in computational analysis, computational methods, numericals. I'm not the right person to tell about these matters. I mean, there are experts. Maybe Professor Vijay Singh knows about it. And of course, there are very, very well-known experts in TIFR who know the ins and outs of these computational methods. So, whatever you said, is fine. Now the question of communicating this is really a very important concern of PER in general, and especially PER at the college level. When I look at papers, some of the papers, even in international journals, they are so much into the technicalities of methodology. Whether this is, and there's very little emphasis on how all this will be imported in the classroom. What is it that you want to tell this in the classroom? So I would say our emphasis has been on that kind of PR, which is less theoretical and of direct pedagogic interest. So I think you should see, sorry, I did not give references to those, but you can see some recent papers of ours in Resonance July 2023, and I think August, something like that, has papers on, they are not PR papers, but they are pedagogic papers. But our idea is, what is that the experts know, but the students don't know, and the teachers can easily know that. For example, physics accepts some kinds of reasonings, and it finds some reasonings unacceptable. So we have one paper on that. What kinds of reasonings are acceptable in physics? And it will take too much time so please go through this. There's some direct consequence in this. For example, we say teleological reasoning. I mean, that's just a word for saying purpose-oriented reasoning. It's not acceptable in physics. Yet in classroom, teleological statements are quite commonly made. I'll give you an example. Every body tends to go to a point of minimum potential energy. It's a clearly teleological statement, as if the body has an inner tendency to reach that. This is not allowed in physics. In physics, the reasoning can never be goal-oriented. In the physics, the reasoning has to be initial. As they say, some initial cause is there for the body to. So, this very common teleological statement should be replaced by the force on a body, the local. We should convert it to a local law. Force on a particle in a conservative field is always in the direction of decreasing potential. That's the proper statement. And what do we say? So it's a force. There's no meaning of tendency or anything with this. Here is the fault, there's a force on it. And here is Newton's law. Force, acceleration will be in the direction of that force. That's all. Saying that it has a tendency to move is not very harmful, but it gives an impression that it has the particle wants to go, as if it tends to go. So this tending statement is not very good. Sodium chloride has run. It likes to throw off its valence electron, and chlorine is as if it's a purpose oriented. They both want to become. That's it. So our language in unintended consequences is not correct. I mean, we tend to use teleological language, and so that is one point. Teachers should avoid that. The other important point is, we have recently in another paper, what kind of frameworks? We just keep telling one thing after another. Sometimes we go to microscopic, sometimes it is probabilistic. What kind of frameworks are there in physics? So some explanatory frameworks. Physics uses certain explanatory framework like microscopic, macroscopic, deterministic, probabilistic, local, global, etc. We have identified such frameworks. And in terms, so when a student is taught action principle, we should say it's a global principle. And the global principle is reducible to a local Euler-Lagrange equation. That's a local principle. Actually, as Feynman also puts in his volume 3, the action principle, almost you feel that it's a teleological principle. Why? What does the action principle say? Particle moves such that at the end of it all, the action is an extremum. Now, this statement looks very teleological, as if the particle has decided that, I mean, its end result is determining what the particle should do. Fortunately, in physics, action principle is not teleological because it is reducible to a local. So the action principle actually is reducible to local Newton's law, you can say, or the Euler-Lagrange equation, or the Hamilton's equations, etc. So these are the points that need to be told. Now, those papers are not PR papers. Those are pedagogical papers. So what I suggest the PR community in India, my suggestion will be, it's my modest suggestion, that we should also write pedagogically interesting. Professor Vijay Singh has been writing a number of pedagogically interesting papers. Pedagogically interesting papers, which are not PR papers, because pedagogically interesting papers are papers in which a good teacher, a very experienced teacher, is sharing pedagogic intuitions with others, with the physics community. PR, what happens is, unless you follow all that methodology, unless the construct validity is true, journals don't accept it or find it very hard to accept those papers. Our epistemic paper took 3 rounds of references, and we ultimately convinced them, because we had such huge data on the fact that the propositions in a mathematical derivations, some of them are definitions, some of them are heuristic, some of them derive from experiment, some of them have a pure mathematics origin. So some steps in a derivation, even a mathematics understand, but a mathematician will not understand every step because there are some steps which are empirical and so on. So please read that paper. It's there in PR. What is the journal? Physics Rev, Phys Rev, PER.
Okay.
But I can confide with you that it took a long time to. But we had 2 samples of data, a large number of data, and the patterns were so consistent, and we got the result that people who have epistemic clarity always do well in content exam. But all those people who do very well, who get good marks, don't have epistemic clarity. It's a clear reflection of Indian education system that you can get marks without much understanding. But if you have epistemic clarity of the kind we define an epistemic score, then the data showed you definitely you always do well. So as is well known, the very top IIT students, they have very good epistemic clarity as well as they are good in merit. But there are people in Indian universities where merit scores are very high, but they don't really understand the content. We are all aware of this Indian situation. So that was very clearly came out. So anyway, to summarize, what I am saying is that, of course, PR is a very important field and people should do it, and there should be advances in PR. It does give you very important messages. And in India is a big country. Such an important discipline must be cultivated to a very large extent. But with that, I would also suggest that pedagogically interesting papers, which may not even have empirical study. There are empirical studies well and good, but pedagogically interesting papers should also be. It is the pedagogically interesting paper that interests teachers. A PR paper, you experiment with a teacher. A PR, he'll get bored after some time. What is all this data and all the person. But on the other hand, if you pedagogically interesting papers is. By the way, this particular thing, therefore, in fact, this paper falls between PR and pedagogically interesting paper. And we experimented with these informally with students at NIUS camps. It's Anvesh did it, I don't know exactly. Some groups he did. And he reported to me that both the students and teachers, where he administered these tests, they said that they are seeing it for the first time and it's very useful. That is the anecdotal thing, not a research data, but there's an anecdotal evidence that these papers teachers would find them useful. So that's yeah.
So there was one question which was coming to my mind immediately when you started talking about this difference between that when we present sometimes Newton's first law of motion in the classroom, we use the word when we state it, that it states that a body tends to be in a state of rest or of uniform motion unless compelled by some external force to change that state of rest or of motion. Now, when we have this word tends in it, does it mean?
No, here it is not, because see, it is local. See, it is when a thing is local, it's talking about a statement. Basically, it's a language, but it says tends to be, if there is no force, it remains there.
Okay.
But it is
Thank you very much, sir.
We should say remains in state of motion.
Yes. Okay. Thank you.
The word tendency, in my opinion, people may have to, should be avoided because it has teleological connection. And in any case, when you say it is going to go somewhere, gives free energy in a chemical reaction is the such, if a chemical reaction proceeds that at the end, if it all gives free energy is minimum. It is as if the chemical reaction has a there's some built-in this thing that it is going to go to minimum. It doesn't make any harm, and in fact, some physics educationists have said that it is cognitively. I mean, it makes for easier teaching, and so it's not terribly wrong. And if you accompany this by the statement that please don't think it as teleological, that is enough.
Okay. Thank you. Thank you, sir.
You continue to make this statement. But the fact that physics does not accept teleology must be told to physics students, which they are never told, and a large number of students are not even aware of it.
So Professor Vijay wants to say something. Sir has raised your hand.
Yeah.
Something very briefly, because I think we have heard a very clear presentation from Professor Arvind Kumar regarding Professor Bhupati Chakravarti's question. There are two issues: whether to use V versus V square, and then there is this amplitude, whether large amplitude. No amount of computer modeling, computer calculations will tell you whether to use V or V square. Yeah. That is an approximation for the model. You make the model first, and then you do whatever calculation you want. Okay, and when you do it numerically, regarding what Professor Ahluwalia said, even there, order by order approximation is important. It's called truncation error, or it's one of the errors in computer numerical calculations or numerical methods. One is the order by order you go to, and the second one is a representational error you make in numerical methods. That is whether the machine is 16-bit, 32-bit, or 64-bit. How many digits are you going to represent the number with? So that's two kinds of errors there. Anyway, thank you. It was a very clear presentation.
Yeah, thank you so much, Professor Arvind. Now I would like to request.
Just 1 minute.
Yes, sir. Yes, sir.
One caution I wanted to tell you that this approximation aspect that we said do not cover every aspect that I have already told you, but one because of the word truncation, it suddenly came to my mind. You see, there are approximations of truncating Fourier series. Harmonic approximation. They are slightly different kinds of approximation than the kind of approximation that we had. So we have not covered all aspects of approximation that which come in engineering on physics. In engineering, harmonic approximation is very, very common in signal processing, etc. I mean, the signal is, you can always break it up into Fourier series, but for actually doing things, I mean, you don't take infinite series, you truncate it at some point. What is the approximation involved here? That aspect does not appear in our paper. Just want to tell you that.
Okay. So thank you very much, Professor Arvind, for such a beautiful talk. I would like to request Professor Ahluwalia to conclude this session.
Oh, thank you, Sapna, and thank you, Professor Arvind, for such a wonderful talk. I think you have opened many, many ideas in this talk for us to follow. And it was brilliantly presented, touched upon a sweep of topics, I would say. And that is what is the great point of this particular presentation. And I hope some of us who are present here, and for those who will see this later on the YouTube also, hope that this will invite them to take up research in this area and take that into the classroom. And the particular distinctions, sir, which you have made in doing physics education research and looking at the pedagogic ideas into the classroom. I think that is a wonderful insight which you have given to us, that what can be very easily taken by teachers to the classroom and what can be, done to satisfy those methodologies of physics education researchers when they want to see the data and validation of all those things. Hopefully, sir, in future, we will keep on interacting with you. We know that you love interacting with the students also. Maybe we can have sometimes a kind of a panel discussion on a certain topic with students in the panel and trying to explore some topic. I am grateful. IAPT is grateful that you found time for us. And sir, may I say that we look forward to your guidance in IAPT as well to carry forward this kind of physics understanding with the community. Thank you very much. And I also thank Professor Vijay Singh for kindly accepting our request to chair this session. Ma'am Rekha is also there. I would like to thank her that she is managing the Zoom platform for us, and the recordings are done and they are made available to the uh, community of physics teachers and students. Thank you, Sapna, for carrying forward this series. This was the 7th lecture, and we
Yes.
look forward to more such insightful lectures in future also.
Yes, sir. Sure,
So,
sir.
thank you, participants. Uh, and maybe the number is small. That doesn't really matter, because today's technology can take this lecture to a large number of people still. So, thank you. Thanks for
Thank
coming.
you.
Thank you. Thank you, Professor Arvind. Thank you, Professor Vijay and Professor Aluwalia, Bhupati sir. Thank you very much for joining us today. Thank you, Ma'am Rekha. Thank you, Ma'am Rekha. And
Yeah.
with this, we conclude the session. Thank you very
Yes.
much.
Yes.
Yeah.
Yes.
Thank you, sir.